Chris Skriniak. I am a partner solutions architect and the global machine learning segment lead for the AWS partner network. This is a special series just for our partners. What we're doing here is walking through each of the built-in algorithms that are part of SageMaker. This is a series, and we will be going through all of the algorithms. And it is even very likely that before we get to the end of this series as planned, there will be more algorithms. What we try to do is provide some insights. We assume little, but we do not assume no prior experience with development with AWS. But we do try to cover all of the basics. So if you're just getting started, if you don't categorize yourself as a data scientist, but rather as a developer, don't worry. This course is for you. If you do define yourself as a data scientist, then I hope there are some new insights and functionalities that we provide as we go through each of our algorithms in this series. So today we're talking about Kmeans clustering. Kmeans clustering, of course, is a part of machine learning that is generally considered unsupervised learning. Were we to take the types of machine learning and just sort of divide them into a matrix, we could take a look, first of all, on the left-hand side, on the y-axis, if you will. There are really two kinds generally of data, discrete and continuous. With discrete data, you have some idea of classification in the terms of, categories, days of the weeks, for example, cats and dogs. It's a discrete entity, and it's relatively easy to identify a particular unit in that entity. With supervised learning, of course, we have classification itself, where we would use, we would discriminate between cats and dogs, etc., hot dog, not a hot dog. In unsupervised learning, we may not have the labels before we start, and that's where clustering comes in. It's really a method for understanding data, doing data discovery, and really trying to glean insights from data that you have. Were all of the data in the world labeled and not messy and not require cleaning up, we probably wouldn't need clustering. But because data is dirty and generally hard to classify from time to time, or the relationships between various features in our data, if they were as clear to the eye as they were, or intuitive as we're looking at them, we probably wouldn't need clustering, but that is really what clustering is for. So unsupervised learning, really is a discovery process, and it's important to approach it with a feeling of experimentation. Now, you don't want to create a mess if you don't have to. So what we start with is really beginning to understand our data itself. Visualizing our data is one of the principal ways of beginning to discover data. When we are working with unsupervised learning, typically we're not too concerned about accuracy. Principal measurements for classification in some of our other methods, the absolute score that is, the most important is accuracy, sometimes to thousandths of a percentage. Not so much with supervised learning. We're really looking for patterns. When we're using unsupervised techniques, structure is learned by the methods that are employed themselves. And typically, we will summarize data and go through the data in a way that produces more insights, as opposed to really sort of focusing down on individual discoveries. And I'm just going to take a moment here, excuse me, just had to review. I saw that there might be a problem with the audio quality, but it seems like maybe we're okay. All right, so when we're doing clustering, we can certainly include a couple of methods for doing clustering, including auto encoders, density estimation, and dimensionality reduction. So there are a number of ways to do clustering. I'm going to cover just a few, and frequently clustering is done in a pipeline. So I'm going to touch just briefly on that. And I also want to point out a few particular problems. Probably the most important one is that clustering methods discover clusters even when your data doesn't have any. So there are a few caveats when you go into clustering methods, and it's important to be mindful before you even get started. So we know now what clustering is from a technology point of view. How do we use it in the real world? Well, principally, data discovery is the #1 method. As a data scientist, what I like to say is you wouldn't do machine learning if you knew the answers to the questions that you were beginning to ask. Unlike ordinary software development, when you're doing machine learning, you don't know frequently what's in your data. So using clustering as a data pre-processing technique is very important. When you're doing clustering, what you will do is begin to discover groups in your data, and then those groups, once defined and a model has been trained, can be very useful for classifying all kinds of objects. Now, those objects may be information that you're looking for in documents, it could be images, and it's also a really important part of search, whether that search is visual or textual. I would say probably the #1 use case, the most common use case for clustering is microsegmentation for marketing purposes. Every business tries to address their customers both in a very personal one-to-one way whenever possible, but also in groups to provide value. Microsegmentation is a very hot topic these days. Not only so that you can communicate through marketing means, which is the typical way, but also for creating dynamic content. If someone is new to your site, they have not made a lot of choices yet about their preferences, you can use the little bit of data that they have provided, perhaps in a login form, or some of the information that might be available just through HTTP methods, and you can begin to provide dynamic content that's more relevant. Another term for microsegmentation is algorithmic personas. And we're not going to cover this too much, but the topic is in this particular seminar, but the topic is so important that it's very likely we'll dedicate another webinar specifically to customer segmentation and dynamic content delivery. Clustering is also used for fraud detection and anti-money laundering detection. It's very useful for going through logs and notifications that are caused by alerts. And as I mentioned before, it's very common in the machine learning pipeline. We're going to touch on that briefly using Spark. So Kmeans. Kmeans is probably the most popular clustering technique. There are others. What K refers to is how many clusters there are in your particular data set. So K is a predetermined number. Before you can run K-means clustering, you have to ascertain with some method how many clusters you think are there. So for example, if you had a collection of handwritten images and you knew that those images were all numbers, 0 through 9, it would be pretty easy to determine that the number of clusters you were going to get to once you've gone through those images would be 10, because there's only 10 digits. It's not so easy when you're taking a look, for example, at your customer transaction data. You know, where do they live? What's their income? What's their standard purchase level? It's sometimes very difficult to determine, but I'm going to show you a method that's quickly evolving for determining in advance what a good number to start is for your clustering. Typically, the way the method works is you take a look at your addressable data space and you place the centroids at random locations. Then you will find for each point in the data set where the nearest point to that randomly assigned centroid is what it's called, and begin to calculate a distance. So for each cluster then, once you've done that once, you will move actually your data point to the average in Euclidean distance to where you initially assigned the first random centroid. So I have a graphic description of that, if that was a little bit hard to follow. So let's say we have a data set right here, and of course it's unlabeled at this point. And we're guessing that there are 2 clusters in this particular set of data. We have an X and Y axis here, so this is just a 2-dimensional view, but you can, and we will actually in today's demo, look at n-dimensional data. So we don't know right now where the clusters are in this group. So we start off by just picking 2 random points, and we calculate the Euclidean distance between them, and then set a line perpendicular to that, the line we first came up with. Then we simply divide. Okay, all of the data sets, the data points that are on one side of that line will go to one centroid. The others will go to the other centroid. Now, the next step is to calculate the mean or the average distance between every one of those points and our randomly chosen centroid. Now, I should have said this initially, the centroid is denoted by the triangle. So what we do is we take that mean number and we relocate the centroid. Once we've moved that centroid to the new mean, we repeat the process again. And we iterate essentially until none of the points within the cluster members are changing cluster groups. So that's the basic methodology. When you walk through it sort of visually, I think it makes a little bit more sense. It's important to note that there will be a handful of anomalies. Some of the data points just don't fall nicely into the clusters that are pre-assigned. So these are typically the sort of grains of sand that we're looking for when we're doing anomaly detection. They may be interesting data points for exploration for other techniques in machine learning. Why are these outliers out there? However, the majority of the data points here have been put into our respective clusters. So were you to have the attributes of that particular cluster in arriving in your data set, it would be relatively easy to act on that data. Now, I mentioned that it's not particularly easy to determine in advance how many clusters you're going to have in your data set. There is a method, it's called the elbow method, where you essentially repeatedly run your K-means clustering for a range of values for K. So for each value of K, you calculate a sum of square errors, and you just graph that. And you do simply visually look to see if there's something that looks like an elbow. On this particular chart, we see an elbow around 3. And that's where, as we begin to add more and more clusters, there's just less and less benefit to adding to the number of clusters. So I have a little bit of Python code here that's, it just sort of shows how that chart was created. It's a simple method and it comes in pretty handy. One warning here, though, is that sometimes it does not produce a nice clean elbow. So you have to just eyeball the data or look for other methods. Now, SageMaker's built-in K-means is not your scikit-learn K-means. It's based on some interesting technology that is a bit custom to what we're doing in-house, but also it's popular in the literature. So in particular, we have 2 means of creating our initial cluster centers. One is called K-means ++, and the other is random, which is the default. So like the original, it scales massive data sets to deliver improvements. I'm having a little hard time seeing my screen here because the webinar control panel's in the way. There we go, excuse me. And the way you change this is actually on the either in Python or in the GUI by setting a factor that that essentially just chooses your means of K-means clustering. We also have an additional factor called the extra center factor, which also increases accuracy. The K-means that's built into SageMaker is made for very large data sets, although it's certainly usable on small data sets. But this ability to do mini batches massively improves the time and reduces the cost of doing your K-means training. There we go. Now, what does the I/O look like? So when you're creating K-means cluster, your data is generally expected to be tabular data. The rows will represent the observations that you want to cluster, and the columns represent the attributes or the features of the data. You can have any number of features, and so there's really no practical limit, but that brings us to one of the next topics, which is how do we know which of those factors are important? So we're going to cover that very, very briefly with PCA, but we may do PCA in a separate seminar as well. Now, how do you create the training job? So you will need to specify the case string. There is a case simply being the number of clusters you expect. You do have the option of adding that extra center factor string. And then you specify the strategy you want to use for that initial cluster center. Now, because there is no accuracy measurement, no validation set is required. So how do we do hyperparameter optimization? And that's where the test data set comes in. So the test data set will emit metrics that depend on the squared distance between data points and the final cluster centroids at the end of the training run. So this can be used to test and create some optimizations around our final centroid values. A range of values are tested by running many jobs. So you can choose tunable hyperparameters, and you would set an objective metric for each of those. I'm going to demonstrate this when we get to our actual hands-on demo here. Now, I've hinted a few times that we might do some dimensionality reduction. We do have a built-in algorithm for that called PCA, or Principal Component Analysis. PCA is very common in data science when you have a data set with many, many features. And that could be anything from a transaction database, say if you have credit card transactions, you're a merchant, and you have all this data around them that includes GPS data, the time of sale, the location of the store, other things that were purchased on the same invoice, etc. And what we'll attempt to do is take the factors in the features in the columns in that data set and determine which cause the most variability in that data set. It will cluster them in such a way that they will begin to combine those features into combined components, where the largest possible variability becomes your first component, the second most becomes your second most, and so on. I have seen some data sets with literally thousands of features, thousands of columns, for example, as you're looking at the data. So that is not the kind of thing you want to run through a K-means clustering. It's very likely not going to produce usable data. But if you could trim that down by both ignoring irrelevant columns and combining columns that combine well to reduce variability, it's a really important part of creating a really effective clustering model. There's two kinds of PCA modes, regular and randomized. Regular is for data sets with sparse data, and randomized would be used for data sets with both a large number of observations and features. that uses another approximation algorithm. Another important thing about SageMaker in general is a lot of the routines, a lot of the algorithms do prefer what's called record IO format. However, comma-separated values is also an option. It's pretty easy to convert your data into record IO format. We're going to see a little bit of that in the code, but you can still use CSV. So what does this look like in a pipeline? Well, first of all, notice that there's, well, not only a spinning sneaker, but a big blue line in the middle of this screen. And that blue line is differentiating between the model training section and the inference section. So sometimes I think of or even describe model training as almost like a compiler, where instead of writing code, you've got data. Your data is in the form of labeled image vectors. In that case, you're really examining the data, looking at the data and creating a clustered model that then becomes a trained model. So in my metaphor or my analogy to a compiler, your trained model is the output, like that executable code, say. But that's all just when you're training. That's just when you're looking at the data initially and you're creating a model. It's not really what you're going to do when you're in production. When somebody comes to your site and you have those handful of attributes and say they want to buy a gold sneaker, and you want to get them to the closest approximation of that object as you have in your online store, for example. So that's where inference comes in. Inference is the real-time production version of your model. It will take whatever you're looking for. Let's say you saw somebody with a gold sneaker on the street and took a photo of that, and you uploaded that image to your online store, and you wanted to find the nearest centroid to that particular image. So that's where you're using clustering in production, and it's sort of a contrived case maybe, but I wanted to separate very clearly for folks who are relatively new to machine learning this critical difference between model training and then inference in production. So once you found that nearest centroid, you found the actual SKU for that sneaker in your database, that's what you then return. You may not have the highly unique sneaker that was asked for originally. So let's take a look at some of this code now. So first of all, I'm here at the SageMaker console. When you go to SageMaker, of course, you have to create a notebook instance to begin to work with. We have some other courses that show you how to do that, how to set that up properly. But just simply notice here that I already have one instance that's already in production. And to start it up, I just click on this open button. Oops, I guess I have to renew my session here. I was waiting a little bit too long. Okay, when you do get to your SageMaker session, you'll be greeted with a Jupyter Notebook browser. If this is, let me just make that a little bit bigger. If this is new to you, let me just show you one or two of the features on this. First of all, it is a browser. Okay, I don't like the messages that I'm getting here. What is going on? That's not good. Let's do this very quickly. Okay, there we go. Sorry for that delay. I guess that's what happens when you're sitting with your notebook open for a little while. Okay, so here's what you see when you go into your notebook browser. Now, I already have quite a few files here. If this is a new notebook for you, you will see a relatively empty set. You'll just see this lost and found directory. Importantly, over here on the, I guess the fourth tab in, we have a number of built-in SageMaker examples. And I like to use these as frequently as possible whenever I'm describing features of SageMaker. I'm going to use these mostly for today's presentation, but I also have one or two that are custom. So what you'll see here is a lot of cut and paste code. is really important to dive into some of these notebooks and take a look at some of the features. When you go into SageMaker Python SDK, we have a notebook here called Kmeans MNIST IP NYB. Now that IP NYB stands for IPython Notebook. And I guess I'm going to have to reload everything now. That's unfortunate. Let me just kill everything. And I guess I'm going to have to start it back up from scratch. That's unfortunate. So I do want to show you, though, quickly how I brought up these built-in or example notebooks up so that you can get running right away. And the way you do that is you open up the SageMaker tab, Examples tab, identify the notebook you're going to work with. The first one we're going to do is this Kmeans MNIST IPYNB. Notice too that there's two ways to look at this. If you're just here to copy and paste code, you can click on Preview. And what it's essentially going to do is give you the code. You could just very quickly copy and paste this, put in the notebook that you're building. Just go ahead and close that, and you're done. You're on your way. If you do want to run this in your notebook, you just click the Use button. So I'm going to go back to my file browser, and I'm going to click on this, which I did have. I did start earlier. Actually, here's the notebook that I actually started. It's Kmeans MNIST. This is a really simple example of using Kmeans to do exactly the case that I described before, where you're identifying 12 handwritten digits. Now, one of the reasons that the MNIST data set is used so frequently is it's very well labeled, it's somewhat well known, and it's also got a lot of dimensionality. Each of the images in the MNIST data set, and there are 70,000 of them, represent 28 by 28 pixel images. And I believe that if you do the multiplication there, that each of those are going to be vectors then of 728, a size of 728. So I'm not going to go through every step. I'm just going to point out the features of this particular notebook. First of all, of course, we have to acquire the data. Next up, we're going to inspect a single cell of that data. We have a small routine here called show digit. Here's the handwritten digit of a 3. We can change that just so you know that there's a whole bunch of digits in here. I'll change that to the very next one, which may not necessarily be a 3. It isn't, it's an 8. Now we go to actually train the model. We have a number of built-in algorithms that are in the SDK, and they're all documented in both on HTTP online and also in a PDF, which I highly recommend downloading. So to call the Kmeans algorithm, we essentially have a wrapper here where we call this wrapper and we have to give it a few parameters. First of all, we're going to say how many instances do we want to train on? What machine type do we want to train on? In this instance, it's a C4 8x large. We do have to specify the required hyperparameters. In this case, we know the number's 10. And we do need to say where the data is. Now, that was defined right here. So far in this notebook, we have downloaded our data set. We have taken a quick look at it. We've told the wrapper where the data set is. Now we want to actually train the model. And in order to do that, we call the wrapper and with its method called fit. I just want to show you in SageMaker now what that looks like here on the console. So in the console on the left-hand side, we have a separate section for training jobs. So unlike maybe other Jupyter Notebook experiences that you may have had, when you're training jobs on SageMaker, your training goes to another machine. Now, one of the reasons we do that is to keep our costs low. When you're in a notebook and you're just editing code the way you just saw me do, exploring data, etc., there's no reason to have, for example, a P2 or P3 instance, which can be very costly. In fact, when I started up this instance, I just used an M4. You can even use a T2, which is our least costly server. So one reason is so that you keep the costs very low. Another is so that when you do your training job, you can send those jobs off to clusters. In this particular instance, I'll just click on this job, which I ran some time ago. And we specified, in this case, we specified an instance count of only 1, but you can train on any number of machines. In fact, we have this notion of infinitely scalable training algorithms in SageMaker. What that means essentially is that we automatically manage our memory, not only within the GPUs, but even out of the GPUs to clusters of machines to train very large data sets. So these are very powerful capabilities within SageMaker. At the bottom of the screen, you can monitor your logs from the training session. I'll just click on that very quickly. And what we'll see is the output that you would ordinarily see in your Jupyter notebook as we went through the epochs of the training. So I'm going to close that window up, go back to my notebook here. We'll see that that same data is a little bit harder to read because it's all kind of comes out in red here when you're doing that training. Next up, we're going to actually host our model. So on SageMaker, we do differentiate between our notebook, our training sessions, and then our production endpoints. When you set a production endpoint, you just use this command called deploy. And once again, you have enormous power here in your options. In this particular instance, we're just setting up 1 server, but you could set that as 10. You can also do production variants to run your incoming data through several different versions of your trained model. We're keeping it simple here though. And notice for all that power that we have in this one command, it only takes 6 minutes and just removes all of that heavy lifting. All right, so now we're gonna validate the model. We're gonna call predict on that model, and we're gonna send it these 2 items from our data set, the ones we looked at above. As we do that, and we can do this one interactively because we do have the endpoint in production, we can see what our clusters turned out to be. Now, Kmeans clustering is not the best way to do image recognition. I mean, we do see in this example here that, you know, it certainly clustered the 0s well. This cluster doesn't look too good. The 3 is a little confusing. But as a very simple sort of off the shelf, well, it sort of nailed the 6s. But you do see that data has been clustered, the images have been clustered. Perhaps if we ran more epochs, this would have been a little bit better. But we do have a soup to nuts example here of how to do the actual clustering on these images. Now, it's very important at the end of any of these notebooks, there's always an option here to delete the endpoint. I commented mine out because I did not want these to be deleted for today's training session. Please do delete these though, because they can be costly if you forget to delete them at the end of your session. Okay, so we're done with those notebooks. I want to dive a little bit more deeply into this process now. We looked at a very high level means of doing Kmeans. We really trusted the defaults around a lot of the process. We do have another notebook here, which is simply called MNIST low level. And what this sample notebook exposes, and I'm just going to go right to it because it's very similar except for one section here, is this section right here. So a really important point of learning how to use SageMaker, getting sort of up to intermediate and advanced level on it, is recognizing that it's built on a foundation of Docker containers. Right here, we're specifying where the Docker containers are actually in ECR, excuse me, for all of our built-in algorithms. Those are just set up in a list here of Docker images. And what I wanted to show here is what all the particular training parameters are for a Kmeans job, what those options are. Now, once again, this is pretty well articulated in the documentation. There are also numerous examples online. But if I go to the console, go to training jobs here again, and just click on the Create Training Job button, you'll be given this form where you can actually see through a GUI what all of those options are. So all of the built-in algorithms are right here, and you can explore those at any time. When we click on Kmeans and come down here to Hyperparameters, we see what all of those options are. So for our training job, for example, we're going to say we're going to give it 10. Feature dimensions, I could be wrong, but I think it's 728. Here's that method for your initial cluster placement. By default, it's going to be random. We can use Kmeans++. If your data set is small, we might want to reduce this. So you get the idea. And then also we have our extra center factor. So these are all things that I sort of mentioned. And a number of other controls, including the various local Lloyd options. So I encourage you to play with this. Everything we're doing here in Python can be done in the GUI. And sometimes going to the GUI can be helpful when you're writing this Python code so that you set your parameters appropriately. Now, here in this section, we have our hyperparameters. We have our K setting at 10. Oh, feature dimensions is 784. That's it. I said 728, I believe earlier, so forgive me, but there it is, 784, mini batch size 500. So the rest of this job is pretty much like the initial job. We do have this method called describe training job. I would like to point out very briefly that all of those commands for monitoring are available from the AWS CLI. So if I type AWS SageMaker and help, you will see all of the various commands, including this describe training job, which is right here. If I copy that and say AWS SageMaker and then describe training job and help, you can see what the required parameters are versus the optional parameters. And this is true. Now, the reason I'm pointing this out is, sometimes it takes a long time to train data, right? So, I like to set this up in a way, let me make that a little bigger so you can all see that. I like to set this up so that I might have a bash shell and a while loop that is checking to see whether the status of that job is done. And then I'll use SNS to contact me, send me a text when my training job is done. This one went fairly quickly in just 4 minutes. And once again, the testing routines at the bottom indicate that we found pretty good clusters, but not perfect. As mentioned, Kmeans is not, you would want to use a convolutional neural network for doing clustering of digits. So we don't always have image data, right? 9 times out of 10, we're working with tabular data. There's a really great blog entry here that's in the AWS blog. And the AWS blog is a great resource for many things. Han Mon created this particular one. And I think it's a great introduction to how you might use 2D data in K-means clustering. It also demonstrates a very, very typical pipeline where you would use PCA to first reduce dimensionality of a particular data set and then use that data set then for clustering. In this example, he uses US Census data for population segmentation and says, I think, quite accurately, whenever elections come up, you want to dig into your data for insights as you begin to, look at how certain counties in the US might be similar or different. And that's exactly what he does here. He uses an open source data set. It's not run by the Census Department, but it includes Census Department data. So I created a notebook, which may or not be accessible here. There we go. I created a notebook from that blog entry. This is not open source yet, but it will be soon. And as members of the partner network, you can certainly reach out to me if you want to get early access to at least my version of this thing. As you can see, first what we do in this notebook is we simply load up our various modules. Nothing too surprising here. We have pandas, numpy, matplotlib, etc. We will go in here and get the actual census data. It turns out that this is one of the many open source data sets that AWS keeps in S3, and it's at this bucket, which is available once again through the CLI, AWS, ML, Blog, SageMaker, Census, segmentation, etc. So we get that data into our S3 bucket, and we just take a quick look at it. And what we see here are states and counties and all of the various population and census characteristics around this data. Now, what's interesting about this is that this is free data, it's open data. Were you doing market segmentation? This is a pretty good place to look when you were looking to enhance the number of features that you had in your data set. Job number one always is cleaning up your data. First thing he does is drop incomplete data in the rows. Turns out only 2 rows drop out. He combines state and counties together, takes a look at just one of the characteristics of that data, where he's taking a look at job types. You can see that there's a pretty strong cluster in this histogram, around say 27% for people that characterize their job as professional, service, or office, but it does run all the way to almost 80% in some counties. Service only goes to 40, and office only goes to, well, just a little bit over 35. So already we're discovering some interesting stuff in this data. Next up, we're using scikit-learn to convert all of the values within our columns to between 0 and 1. It's a very, very common practice when you use pandas describe. We can take another look at this data, and we can see this all now has been scaled between 0 and 1. All right, let's skip ahead now to PCA. So just as in the first example, where we have a built-in function that calls Kmeans, we have one for PCA. Here we're specifying how many machines we're going to run our training on, just one. We're going to do it on a C4, no GPU required. And we are specifying the number of components that we're looking for. We're also going to specify that all our data is float 32. And what comes out of this, let me just scroll down a little bit. Oh, I don't want to skip this part though. What comes out of this, once our job has been trained, this is actually the main reason I'm showing you this particular notebook. Once our model's been trained, we need to open up that model and take a look at the individual components. In this particular case, in a pipeline case, we don't just care that we create a well-trained model, we actually need to look at the coefficients for the actual data so we can determine which parameters we want to use. Now, because PCA is built on MXNet, we can use MXNet utilities. All we have to do is load up, well, first we have to import MXNet. Then we load up the trained model. And from that trained model, which is just going to be an ND array, we can pull out these 2 metrics. And as it's described here, V is going to be our principal components, and S is going to be the singular values for the components that were created in that PCA transformation. And just to move down here just a little bit, we could see that component number 1, which is our most powerful component, has these particular characteristics. It is predominantly Black and Hispanic, very low white population, income is low. So this is obviously a pretty important variable. We don't need to look at all 32 variables. In this particular case, we're just going to look at the first 5. Now, we know from looking at this data what components were combined. In this case, component 1 is poverty and unemployment, self-employment, public workers is number 2, and etc. So now, in order to use this, we need to deploy it. We need this as an endpoint. Now, this is not an endpoint in our case that we're going to make available to the public. We're not going to attach it to API gateway or anything like that. We're just going to use it for our internal purposes in this pipeline. We run our data against that model, and we have some interesting results here, right? So this is, now we could take our original data and run it against that PCA. Once we've done that, now we can begin to use our transformed data and do some clustering on that data. So just to remind ourselves, what we're trying to do here is look for similarities and census characteristics between all the various counties in the United States. So we've trained our PCA, we've run our original data against the PCA. Now we're creating a model and deploying that model with Kmeans. And now we're going to run a prediction against that model. What we see is we specified that we were going to look at 6 particular components. And we can see some, now we need to visualize some of the differences between these components. And here's where the reward is, sort of at the end. When we take a look at and we extracted this data from our model using the exact same technique that we did for PCA, right? We used our MXNet tools, and now we can examine all of the individual characteristics. This information is a little bit hard to glean right now, so I'm really happy that I talked to the folks in-house here and got a copy of this notebook to share with our partners today. Because one of the questions that I've come across frequently since SageMaker was announced was, hey, it's great that we created these models. I want the coefficients. Well, here's how you get the coefficients. They're right there. All right. Last but not least, we can create a heat map out of these coefficients where we take the principal components and map them against the clusters. And we can see there's some broad differences here in cluster number 3. I might want to look at cluster number 6 as well. So down below, we take a look inside, and what we actually see here, well, actually here in this particular instance, we're looking at cluster number 1, and we're taking a look at the head of that particular cluster. And we can see, surprisingly, that California, New Mexico, New York City, South Dakota are all in this exact same cluster. So these counties have very, very common characteristics given by our top principal components. So that is those are the notebooks I wanted to take a look at to sort of illustrate the built-in algorithms. Before we leave, and I certainly hope we can see
Chris,
this.
we have a question. So I want to hand over to Valkvekar. Please go ahead with the question, sir. Vaibhav, yes. Please proceed.
I will stop speaking when I hear the question come in. What I'd like to do very briefly before we go to our Q&A, I wanted to save the last, well, 10 minutes, but I guess 8 or 7, as the case may be, is how do we create this from a Spark pipeline? Now, many folks are familiar with Spark and the ability to use Spark in a pipeline manner. There is a notebook that comes with all of our instantiated SageMaker instances. It's called PySpark, MNIST, PCA, Kmeans. And I love this illustration here. It very clearly illustrates that from your internal data in your training data frame, you can call one of the SageMaker algorithms, PCA, SageMaker estimator, to then go to SageMaker Kmeans estimator. So you're actually within your Spark pipeline here, but then calling SageMaker built-in algorithms. So if you are a Spark user, this is a really explicit example. Once again, using the MNIST data set, which should be very familiar. But it's a great example for integrating SageMaker with Spark. So, so that's all I wanted to go through today. I did have just 1 or 2 more things here that I wanted to cover. Very briefly, there are other clustering methods. One in particular is tsne. And because we are working with the MNIST data set. I just want to bring this up very quickly. TensorFlow has a great projector that has the MNIST data set with images built into it. And of course, it does PCA, which is the default here. But while we go to Q&A, I wanted to start a tsne clustering of that particular data set. And we can now move to questions while we watch that form. So I am ready for questions. And let's see. Trying to get the GUI up here so I can see questions.
I would like to remind everybody that questions can be entered in the question tab, also on the chat directly, or you may raise your hand in order to ask us the questions verbally.
So while we're waiting for questions to come in, and please interrupt me at any time, you can see in this, one of my favorite visualizations here, the individual handwritten characters being sorted through the tsne algorithm. Now, tsne was created by Geoffrey Hinton specifically for the clustering of high dimensional data, of course. Okay, great. So here's one question that came in. Is that the only notebook which is integratable with the Spark pipeline? So for example, can you use Zeppelin? I don't know the answer to that question. In other words, I don't know if we enabled that through a quick start or something. I mean, certainly you can integrate Zeppelin with Spark. But it's certainly not one of the default setups that we have here. So whoever asked that question, if you do follow up with me in email, I'll see if we maybe have a quick start to do that. Now, of course, that may not, it may not be as easy to do SageMaker integration with that particular configuration. And I'll also say I personally have never done, I've never used that configuration. We're certainly open to other questions. You can also color any data. You can upload your own data using the technique that I showed you with our ability to pull components out of our models in SageMaker. You can upload your own data set and put it into this visualizer. And I see that we do have someone with their hand up. You can certainly ask questions if you like. Pratap, maybe you can help me a little bit with this.
We have unmuted Azar Khan. Azar, please proceed with your question. Azar, you're connected to audio now. Please proceed with your question.
We may be having a technical difficulty here, so certainly type your question if you do have it. One more thing I would like to mention, these are not SageMaker algorithms, built-in algorithms, but tsne, of course, is available through TensorFlow and other frameworks. Also, just in scikit-learn, I'd like to mention briefly agglomerative clustering. Agglomerative clustering can be very useful in demographic analysis because it is hierarchical. So you can see from this dendrogram that's given on this particular example here that you may not only be able to have the individual clusters at the ends of these nodes, but also as you go into the various heights of the dendrogram, you may be able to classify for your microsegmentation models using these all these various methods. So Obviously we're focusing on our built-in algorithms on SageMaker today, but because SageMaker is open and we're non-denominational in the way we do almost everything here at AWS, you're certainly welcome to import other frameworks and use them in tandem or in combination with SageMaker notebooks. So we're at the bottom of our hour here. I'll maybe pause for a few more seconds, see if we can get these questions in. Oh, great, we got another one. Okay, so here it is. Can you use RStudio with SageMaker? So, Sarge, there's some great quick starts that will start up RStudio on EMR, which is, of course, our Spark Hadoop service. But no, you can use R in SageMaker. There's a built-in notebook that loads up R, and we have plenty of R examples, but RStudio itself, no. All right, so we're at the end of our hour here. I hope that that was enlightening, and no matter where you're coming from on your journey into machine learning, I hope you found some strong value. If I prompted other questions, or if there were if you weren't able to get in through our interface here, I hope you will please reach out to me at my email address. I'm a partner solutions architect, so I am here to help you guys out. Someone just got one last question in here. Where do we get the notebook for the census data? Just send me an email. My email address is right there. So I'm more than happy to provide.
I put the URL for that blog in the chat window. So
you put it there. Oh, fantastic. Bravo.
I believe the question came from Hemant. So Hemant, you can just look in the chat window and click. We have Azar is asking the question now. How much customizable is SageMaker through the SDK, and why there are two different variants of the API, i.e. Through AWS SDK and separate SageMaker API?
Okay, so as far as customization goes, it's highly customizable. We're going to go through our built-in algorithms first. It is important to note, if you are an ISV, if you're in business selling software, especially software as a service, you can start a SageMaker Jupyter notebook directly from your product. You can launch it right from your product and do integrations with your data directly from the product. So eager to talk to you about that. As for the different methods of access, of course, we have the various language SDKs. We have the Bash interface. We have the GUI interface. And the reason we have these is because workflows are different in different environments. Many of the features are identical across the different APIs. So they're just designed this way to enable a workflow that's best for your environment.
All right. All right, I would like to thank everybody for the participation today. We will soon be in contact with you to organize the third SageMaker deep dive. We hope that you have enjoyed the presentation, and we look forward to speaking with you soon. Thank you very much.